All right, section 2.1. We went over, we looked at matrices as an array of numbers and we did things to it. We treated it like it was, like a vector had some sort of magnitude and direction. So we want to know what kinds of interesting properties we can get out of matrices. Um, we'll, we'll dive into the properties a little bit later, but we want to treat them like they're things to manipulate, just like whole numbers are to manipulate, and then functions. We got more advanced. We started manipulating functions, and then we started manipulating vectors. So we want to know what kinds of algebra we can apply, or arithmetic we can apply to these things. And so for matrices, the first two basic operations we studied were addition and scalar multiplication. And so the whole idea of subtraction is like a scalar multiplication with addition, where you're scaling it by -1. So kind of falls under that property. And the next one after that was matrix multiplication, which was a little bit more complicated. And then after that, the third thing that we went over was the transpose. I mean, if we call addition and scalar multiplication one thing. So here are some basic properties for addition and scalar multiplication combined. We have addition is commutative. And associative. So those basic properties of real numbers that we've known back when we were in second grade. Did you know them back in second grade? No. But you were using them, right? So I'm teaching math for elementary school teachers, and we're talking about commutative and associative properties and stuff. And so how kids learn to use the commutative and associative properties. When you're adding 15 and then you're adding 13 plus 7, instead of adding 15 and 13 first, you would automatically want to add 13 and 7 because they add up to a nice number, and then you tack on 15. So in your head, you're kind of using the associative properties. So that's what kids do. That's how we teach them how to add and subtract and stuff. So those properties. We have the identity property of addition. The zero matrix is a matrix of zeros. Depending on what it is you're comparing it with. If you're adding it with a 3 by 3 matrix, then your zero is a 3 by 3 matrix of zeros. So this is, in formal math terms, the additive identity. And then we have a couple of distribution laws, distribution for scalar multiplication. So whenever you start involving addition and multiplication, we try to search for these distribution laws. So distribution law, where you can distribute a scalar over a couple of matrices, and then a distribution law where you can distribute a matrix over a couple of scalars. So they might come in handy for different things that we might take a look at and try to prove or whatever. And there's also another associative property for this time, instead of 3 things that you're adding, the scalar multiplication has an associative property where you can combine the scalars together and multiply it with a matrix. So those are your basic properties for addition and scalar multiplication. Now let's go to matrix multiplication, when you're multiplying 2 matrices together. We have an associative property. Notice that usually when we have a list of properties, we start off the commutative property, right? So it turns out that matrix multiplication is not necessarily commutative, so we want to point that out in our next level here with the warnings. But it is associative under multiplication, which means you can regroup the matrices to whatever might be more convenient. We have a couple of distributive laws, and one of them is being multiplied on the left side, the other one's being multiplied on the right side, so they are called left and right distributive. If you want to give it a name. B and C is that we're multiplying a matrix. We're doing a distribution where the matrix multiplication is coming from the left side, and then the other one is a matrix multiplication where the multiplication is coming from the right side. And because matrix multiplication is not commutative, we have to acknowledge those two different ideas separately. um, we have another associative property with matrix multiplication involved in a scalar. And it's a weird property to describe because it's almost like distributing, but it's not really distributing. It's just associating your scalar with a product is the same as associating your scalar with one of the matrices separately and then doing the multiplication. So it doesn't matter which one you do, do the association as long as you're keeping the matrix A on the left side and matrix B on the right side because of the matrix multiplication non-commutativity. So these things really come up when you're proving things, and R might be an actual number that you're multiplying out, but then A or B might not be numbers or whatever. In any case, we have that property, and then we have the identity property of multiplication or multiplicative identity. So the one we think of, anything times one is whatever that anything is in real numbers. When we're talking about matrices, our one is often called the identity matrix. And so we denote it with I, and then if we need to be clear about what the size of this identity matrix is, then we put a sub n or sub m, depending on the size. At this point, we're not saying that A or B or C are particular size matrices, and so we want to account for that by putting the appropriate size of the identity matrix. And sometimes identity matrix in some of the books that you might come up with, sometimes identity matrix is denoted with one, the number one, and then they put an N or an M subscript, and that's going to mean it's the identity matrix. And the identity matrix, we talked about this last time, is a matrix where it's ones in the diagonals and zeros everywhere else, and it has to be a square matrix. Identity matrix is always a square matrix. Okay. All right, now we have to, because of certain rules for multiplication, we have to be careful about things that might come up that might seem normal to us in real number talk, like commutativity and stuff like that. So we need to make sure that's highlighted and we understand that some of these rules don't work naturally for multiplication. So first of all, in the warnings, the first one is that AB is not necessarily equal to BA. It's not commutative. And so because it's not commutative, the idea of the cancellation law might not work out. If AB equals AC, then you can't just automatically cancel A. And that fact will be discussed today when we talk about inverses. And then there's this idea that we had also with, especially when we were solving quadratics and factoring and stuff like that in algebra, where if two things multiplied together is equal to 0, then that means one of them has to equal to 0. Right? That's a zero factor rule or zero factor property that we might have learned in. If you don't know the name of it, you've definitely used it in the past. So that fact doesn't work here either. Just because A times B is equal to 0 does not mean that one of those is a zero matrix. They could be both non-zero matrices, and then when you multiply them, you get 0. So it could happen that way. So there's these warnings to watch out for. They all involve multiplication. Okay. Any questions? All right. The third thing that we talked about or we learned last time was the transpose. And remember the transpose, you switch the rows and the columns. That's the basic idea behind the transpose. So if you switch the row and the columns and then you switch the row and the columns once, you can get back your original matrix. So the first property says the transpose of a transpose is the original matrix. Makes sense. The one that's not so obvious, there's a few others here that might not be so obvious. The second one, I think it's not very obvious, but when you work it out, try it out with actual matrices or just your A, B, C, D matrix or something, it turns out that the transpose of a sum is the sum of a transpose. So doing the transpose first on each one and adding them is the same as adding them and doing the transpose to your result. So that's an interesting idea. That again, if you have a simple 2x2 matrix, you can try it out and see what happens. A transpose of a scalar multiplication is the same thing as moving the scalar out and you're just taking the transpose. That one kind of makes sense too. Again, imagine your matrix A, B, C, D, 2x2 matrix multiplied by 5, and then do the transpose. Factoring out the 5 would give you the same results. Now the last one is another one of those that's not so obvious, that the transpose of a product is equal to the product of the transpose, but it's in reverse order. What? Yeah. So we can do a simple example, 2x2, maybe, just to kind of see that come out. So let's let A equal to 1, 2, 3, 4. Let's let B equal to, I don't know, 0, 5, 2, -1. So what we could do is we can multiply these together and then take the transpose and then take the transpose and do them separately and then compare them to see that we're going to get the same answer. So let's do AB on this left side. So 1, 2, 3, 4, 0, 5, 2, -1. Just to remind you of how multiplication works. 1, 2 multiplied with 0, 2. When I say multiplied, it's kind of like dot product. So 1 times 0 is 0, 2 times 2 is 4. All right. And then 5 times 5, 1 times 5 is 5, 2 times -1 is -2, 5 minus 2 is 3. 3, 0, 4, and 2 is 8. 15 minus 4, 11. Did I do that right? All right. So the transpose of that is equal to what? Is equal to 4, 8, 3, 11. Okay. All right, now let's check the other side. We have B transpose is equal to 0, 2, 5, negative 1. And then A transpose is equal to 1, 3, 2, 4. So multiply them together. Do the multiplication again. 0, 2, and 1, 2, that gives a 4. 0, 2, and 3, 4, that's 0, and 2 times 4 is 8. And then 5 times 1 minus 1 times 2, that's a 3. And 5 times 3 is 15. Negative 1 times 4 is negative 4. It's 11. And we see that they're equal to each other. It's not a proof. For a more general proof, you can try to write A and B as general matrices and then find a way to do a multiplication over general matrices. I think they use column vectors for their multiplication in the book. All right, so that's an interesting property that would come in handy for us. And if you were to try to just multiply A transpose times B transpose, you'll see that it's probably not going to equal to that since it's not commutative. Okay? Any questions? You want to see that's not equal? Looks like I have MATLAB up. What's this? Oh, I was trying to do some programming. Let's see. A, what was our A equal to? A equals 1, 2, 3, 4. B equals 0, 5, 2 minus 1. And so A transpose can be written, transpose, remember, in Octave or in MATLAB is with an apostrophe. B transpose. And so A transpose times B transpose. And if you do the multiplication with just the regular star, that's your regular matrix multiplication. And the component-wise multiplication is with a dot star, right? So anyways, the answers that we got here is different from B transpose times A transpose, which was the correct answer that we were looking for. Okay. So that's how you can, well, this is how you can use MATLAB to do your matrix multiplication for you. All right, any questions? So we're all experts with addition, scalar multiplication, matrix multiplication, and transposes. Yes, we're moving on. Oh, yeah, yeah. Was powers done in 2.1? Yeah, yeah. Oh, yeah, they stuck it in there. Yeah, yeah. I suppose we should mention powers. I don't have any more room here. I'll sneak in a page. So what can we say about matrix powers? Yeah, it just works like normal exponents, right? So a to the n power is equal to a times times A and times. So remember when we're doing the multiplication, um, A times B, A has to be, if this is an n by, or m by n, these two things have to match up, right? So what does that mean for your A matrices here? They all have to be square matrices. So A has to be a square matrix for this to work. Okay? If it's not, then it's not going to work. Mm-hmm. Yeah. So a lot of those would work. Oh, I put the wrong one up there. That's why it's not the same size. Sorry, I need to adjust my size for the notes. Oh, that didn't work. All right. So um, as long as you have a square matrix, then we can write that property that Ryan was talking about. A to the n times A to the k is A to the n plus k. And I think most of those other power properties would work. We're not dealing with divisions. We have not defined division here. We're not going to define division, so we don't do that dividing business. But we can do this, and we can take a power to a power. So we at least have these two properties that we got from back in real numbers that would work for multiplication. No, because you can't multiply. If it's not a square matrix, then the first, when you square it, just squaring it, it's not going to work already. So we already have an issue there. Yes. So the negative business we'll do after today when we study inverses. So at this point, we can't do that yet. We don't have that specially defined. So there's no division. So we can't do that yet. But we'll take a look at negative powers. But the zero power is another one that's also popular. So a to the zero power is the identity matrix, just like in real numbers. Okay. Since we have MATLAB here, and we have A, we try a couple of things. A raised to the zero power identity matrix, right? A raised to the second power would just be A times A. So you get the same result. And then to the third power, A raised to the third power, and then A times A times A. You get the same result. Okay? And if you have a non-square matrix, we don't even have to try it here. Just imagine a 2 by 3, multiply that with a 2 by 3. That's not going to work. um, yeah, so that's why it was a short things, because that's all there really is to say about it. Until we start looking at negative powers and stuff, then that becomes. By the way, if there's a component-wise in component-wise multiplication. There's also a component-wise power. If you do a dot in the power in MATLAB, then it's going to take each individual entry and then raise it to the second power. So instead of 1, 2, 3, 4, we would have 1, 4, 9, 16, right? So apparently that's useful for certain things when you're dealing with just arrays in general, but when we're dealing with matrices, we don't want to use this. We always want to use the idea of matrix multiplication when we're dealing with powers. Okay. Yeah. So a raised to the -1 power is the inverse of this. And that's what we're going to do today. Half an hour later. All right, good. So I thought I adjusted my window. A lot of blank space here. I feel like we should do some examples. Yeah, let's just move on. All right. So today we're going to deal with inverses. So here's the formal whatever is written in the book. If you have an n by n matrix, it's set to be invertible if you can find another matrix C such that C times A is equal to the identity. And also, since matrix multiplication is not commutative, we also want to allow for A times C to give you the same result. I think I know what you're going to ask, Nate. Oh, because it has to be a square matrix. Yeah, the size of the matrix has to be a square matrix. So the number of rows and the number of columns have to be the same. So we don't have an inverse for non-square matrices, I guess is the answer. So they include a random matrix C, but then eventually they say that matrix isn't so random, that it's unique. And then so they give it a special name after all the definitions said and done. But in the end, we're just going to call it A inverse with a negative power. That matrix is unique because if you were to come up with another possible inverse like B, then they say B is eventually going to equal to C, which makes it that very same matrix. So the matrix, if the inverse exists, that inverse matrix is actually unique. And there's only one inverse for a particular matrix. In other words, you can't have two different inverses for the same matrix. And so after they figure that out, then they have the notation for the inverse, and that's A to the -1. So we don't want to think about it as division. In a way, when we see equations, it looks like, oh, that's pretty much what we do for division, because division is not defined. Only matrix multiplication. And so in matrices, whenever we're doing a division kind of, and I say division in quotes, whenever we're doing a division kind of activity, it's really a matrix multiplication with the inverse. So there's a great amount of studying whether a matrix is invertible or not. And so they gave special names to that. If a matrix is invertible, then, well, they start off with the matrix is not invertible. It's called a singular matrix. And if it is invertible, then it's non-singular. They don't use non-singular so much. If it's invertible, they just say it's invertible. If it's not invertible, then they say it's singular. So the word singular is used a little bit more so than non-singular. But they're terms. Okay. So let's take a look at, since MATLAB did some work for us already, -2, 1, 1, that would be a -1/2. So for our generic matrix, A is equal to 1, 2, 3, 4, it turns out that A inverse, according to MATLAB, is 1, -2, -3, 1/2. Wait, what was it again? 1.5. That would be 3/2, right? 1.5. Did I get? Oh, so those are negatives, and that's not. Okay. Boy, I bit this one, huh? All right, let's try it again. This is a what? I forgot now. -1, +2, -3/2, +3/2, -1/2. Okay. Let me just check one more time. Yeah. Okay. All good. So let's do a matrix multiplication. Let's multiply these two. Um, A inverse, 1, 2, 3, 4, -1, 2, 3/2, -1/2. So if I multiply the rows and the columns, I have 1 minus, oh, this is -1. What? All right. So -1 plus 3. What's -1 plus 3? 2. That didn't work out. Let's make sure we copied it correctly. Oh, it's -2. All right. This is getting ridiculous. Can't even remember these things. Yeah, I can't remember 4. It's just 4 numbers. Jeez. I was never very good with numbers. We have a 2, -2. See, I messed it up already. 1, 3/2, and -1/2. All right. -2, 1, 3/2, -1/2. All right, let's try it again. So this is a -2 plus 3. That's a 1. And this is a 1 plus -1, right? 2 times -1/2, 0. And this is a -6, -6 plus 6. So that's a 0 again. And then a 3 minus 4 divided by 2 is 2. 3 minus 2 is 1. Whew. I don't know if I want to do this again. And then if you switch it and you go through the trouble, you're going to get the same thing, right? So if C was the, wait, what? Oh, not the transpose, it's the inverse. C equals the inverse of A, then A times C and C times A should equal to the identity. Okay? Now, how do you get the inverse? Experimentally. Yeah. Well, it turns out that at least for 2 by 2 matrices, the inverse is actually a nice package formula. So uh, let's get that down. Well, we can explain how we do it, or we could just get the result and then multiply it, and then see that you get. Sure. So in a few minutes, we'll talk about the algorithm to actually find a more generic, generic size, 3 by 3, 4 by 4 matrix, and find the inverse of those types of matrices. But for now, let's just enjoy this because it's a formula for us. It's given, so let's just make sure we know it. For 2 by 2 matrices, it's 1 over this thing. This thing, what's that? Oh, it's a determinant. Oh, what's a determinant? I don't know. Ask Professor Tong, right? uh, the cross product is the determinant of a matrix, yeah, but the determinant isn't necessarily a cross product, yeah. So the determinant is just, again, my answer for Delilah asked this question in the other class that was doing determinants. Um, it gives you a scalar value that would somehow describe this matrix. It's kind of like a ranking. For vectors, we can find the length of the vector by doing something to the vector, and that length is like a real number value that describes a vector. So I don't want to say that this is a length in quotes. You could do that too. But in terms of matrices, it gives you a numerical scalar quantity that's unique to this one matrix. It describes some stuff too, and we'll talk about one of the things that it describes in terms of invertibility, since we're talking about inverses. You could see that if AD plus BC was equal to 0, then this thing's not going to make any sense, right? Because you'll have a 0 in the denominator. So having an inverse and the determinant being equal to 0 is going to have a close relationship that we'll get to see later on. But we're not going to study determinants until like chapter 4. So this is just a quick definition. This is a determinant of a 2 by 2 matrix, and then we'll be done with determinants for now until we study eigenvalues and eigenvectors. So yes, a down here. Ooh, yeah, sorry, typo. This is also AD, all of them. Damn, copy and paste. Really? Might have been on my second scotch when I was typing this. All right. Do we clear the air here? All right. So let's check our A matrix and how MATLAB was able to get this -2, 1, 3 halves, and -1/2. So if A was our matrix 1, 2, 3, 4, then our A inverse, according to this, should equal to 1 divided by 1 times 4 minus 2 times 3, or 3 times 2, times, and then here in the diagonals, the diagonals get switched. So instead of a 1, 4 in the diagonal, I have a 4, 1. And then the wings, or I call them the wings, they get negative. They get negatived. They get negated. Yeah, that's the word. I knew there was a word for it. They get opposited. What? So 4 minus 6, is that negative 2? So negative 1/2, 4, negative 2, negative 3, 1. And that gives your negative 2 for the first component. And then 2 divided by 1/2 times 2, and then positive, negative is positive. This one is a positive again, but it's 3/2, and this one will be negative 1/2. And that's exactly what they had up here. Right? So now whenever it's not just magic, it's not just MATLAB. It's it's uh, it's a formula. Well, there's that's great for 2x2s, but now if we have a 3x3 matrix, we need something more sound and more like an algorithmic way to find our inverses. So how are we going to do that? Oh, I guess before we do that, there's there's some properties. Where's the algorithm? Here's the algorithm. All right, let's talk about 2x2 matrices first and talk about some of its properties. Sorry, I left my script. The first one isn't so much of a property as more like the importance of or another point of view of matrices. And remember that whole idea about dividing back in algebra? Whoa, sorry, what happened? Back in algebra, we have like an equation to solve. We would solve for it. I guess I should have just been. Uh, that's too hard. Let's get something easier. So we do it by dividing, right? We divide by 2. We can also think about it as multiplying by 2 to the negative 1 power. And since in algebra and with real numbers, it's commutative, the whole idea about dividing it doesn't matter which side you divide it on. In any case, we have x is equal to 2 to the negative 1 times 4. I mean, So if you know the inverse to a particular matrix, then you can solve for your ax plus b equations that we've been studying. And you can solve for it by saying x is equal to a inverse b. But note, because of the properties for non-commutativity of matrix multiplication, a inverse b is not the same as b times a inverse. So I know that's kind of like what I did. That's what we would do. It doesn't matter whether you multiply it on the left side or the right side of an expression when we're dealing with real numbers. But when you're dealing with matrices, it does matter which side you multiply it on. So when you say A inverse B, it's not automatically the same as B times A inverse. So I suppose we can come up with a really simple problem, or simple, I don't know about simple. See if we can come up with an example for this. Red is too bright, too green. And we'll keep using our 1, 2, 3, 4 matrix. X plus 2y is equal to 7, 3x plus 4y is equal to negative 1. I don't know. So this can be translated into ax is equal to b, right? Where A is our original matrix that we've been dealing with. X is your xy vector, and your B vector is 7, negative 1. So we know the inverse of this, so we can immediately just jump to the answer. Your x vector is equal to A inverse, negative 2, 1, 3 halves, negative 1 half. And so we can just solve for this matrix multiplication if you already know the inverse. You know, chances are you're not going to know the inverse, and doing your solution for ax plus b or ax equals b this way requires you to know your inverse. And so finding your inverse is a problem in itself, and generally that's more difficult to do than just to do the row reduction. So it might be handy though if you have to find the solution to this for many different b vectors, over here. So in any case, simple matrix multiplication here is going to give us, negative 7 minus 1, that's negative 8, and then negative 7, or no, 21 halves plus a half, 22 halves. Negative. Probably. Negative 15. And then let's try this again. 21 plus 1, 22. 22 over 2, right? 11. So now we have a solution. Well, let's check our matrix. Let's let M be the I'm gonna augment the matrix. So we're gonna augment the matrix A, and then if I just do a space and then put in another vector, 7, 1, 7, negative 1. Then it's the augmented matrix, right? And then I'll row reduce to find the solution. And then we got negative 15 for x, and then positive 11 for y. So that's the solution that we got by row reducing using the augmented matrix. And then this is the solution we got if we knew the inverse, the inverse matrix. Okay. All right. So let's take a look at some more properties of invertible matrices. So properties of invertible matrices: if you have an inverse, then the inverse of the inverse is the original matrix itself. Kind of like the transpose, huh? Transpose is the original matrix. The inverse of the inverse is the original matrix. And that makes sense, I think. Yeah. If you have two matrices that are the same size and they're both invertible, then the inverse of the product is the product of the inverse in reverse order. kind of like the transpose. So if we have A and B are two matrices, and they're both invertible, then the product is also going to be invertible. And the inverse of the product is the product of the inverses in opposite order. Just like the transpose. And it turns out that if you have an invertible matrix, then the transpose is also invertible, and the inverse of a transpose is a transpose of the inverse. They seem like intimately connected that way. Right? They have the same properties. You know, the first two properties are the same properties that we saw for transposes. So now it seems like we can interchange transpose and inverse. You can't. Just the operations. And so that last one puts those two operations together. So if you have a transpose, you want the inverse of that, you can take the inverse of the original matrix and then take the transpose of that. Interesting. Any questions? All right, let's see what else is in my notes before we get to the algorithm. Oh, elementary. Oh, this is a whole page. Maybe we can see if we can come up with some examples here. Oh, so number 7 is a good example of why you might want to find the inverse to solve for your AX equals B. I don't want to do any examples. Let's keep going. Elementary matrices. So elementary matrices is what's going to help us put our algorithm together. Yeah. Yes, maybe. That should be a yes or no answer. Yes. Yeah. It's a secret. No, it's going to be covered in chapter 4. So we're going to have all kinds of list of equivalences for what it means for a matrix to be invertible. And we're not going to see it today because we haven't really fully discussed determinants. But if your determinant is non-zero, then your matrix is invertible. All right, so elementary matrices. Let's take a look at what elementary matrices are. So an elementary matrix is a matrix that you get when you do an elementary row operation on an identity matrix. All right, seems pretty basic. There's only 3 row operations. I mean, the third one probably, there's a scalar multiplication, so you can scalar multiply it with anything. But there's only 3 elementary row operations if you remember them. So one is a switch. I was thinking that was the last one. And then scalar multiply row, just a row, not the whole matrix, right? There's a difference when you scalar multiply a row versus the whole matrix. Here, scalar multiply. Just one row. So for 2 by 2 matrices, I think it's easy enough to gather all the possible elementary matrices that we can come up with. Let's see. So for a 2 by 2 matrix, you're always starting with the identity, right? So elementary row operation 1 can be described as your 1, 0, 0, 1 matrix. This is your identity matrix. And then you want to switch the order. So it becomes 0, 1, 1, 0. E2 could be just multiplying the first row by any scalar. We're using R for scalar, so let's use R. I mean, you can use 2, 5, 7, negative 15, whatever. But just multiplying one row, it doesn't have to be the first row, it could be the second row, but just by multiplying one row by a scalar, that's an elementary row operation, right? And then another example for the third type of elementary row operation would be multiplying the first row by a scalar and then adding it to the second row. So what are these elementary row operations? We can think about these elementary row operations as this is switching row 1 and row 2. I think that's the symbol that we use for a switch. This is multiplying row 1 by a scalar. And then this one is multiplying row 1 by a scalar and then adding it to row 2. Yeah, we could do that. So anyways, so these are 3 elementary row operations for 2 by 2 matrices. Let's look at this second paragraph here. What does it say? If an elementary row operation is performed on an m by n matrix, then the resulting matrix can be written as E times A, where the m by n matrix is created by performing the same row operation on the identity. E is one of these elementary row operations, and it has to be a square matrix because it comes from the identity. But A does not necessarily have to be. All right? So let's come up with some numbers there. Let's take a look at what they're saying. Let me define these matrices first. E1 is equal to 0, 1, 1, 0. E2 is equal to, let's pick a number for R, 2, 0, 0, 1. And then E3 is equal to, let's pick a number for S, 1, 0, 3, 1. So those are the matrices that we're dealing with, right? Let's take a look at a non-square matrix. I think we have M as a non-square matrix, right? So let's imagine switching the rows for M. Do that in your head. You see what the matrix is if you switch the rows? Okay, now let's multiply E1 times M. E1 is that matrix that switches the rows, right? So when you multiply this, according to that paragraph, when you multiply this, you should get M with your rows switched. Did it work? There we go. It worked. All right, let's take our second elementary row operation matrix. It multiplies the first row by 2, right? So let's imagine multiplying this with M. Wait, here's M. So imagine in your head multiplying the first row by 2. Did it work? It worked, right? with that elementary row operation matrix. And then the third one, we said that we took the first row, multiplied it by 3, and added it to the second row. So this is a little bit tougher, but look at the first row, look at your M matrix. Multiply the first row by 3 and add it to the second row and replace the second row. What are we going to get? 3 plus 3 is 6. 6 plus 4 is 10. And 21 minus 1 is 20. So E3 times M. 6, 10, and 20 in the bottom row. Okay? Feels like it's magic, huh? Look, no, got my sleeve. Just comes out like that. So, elementary row operations, multiplying it on the left side, because it makes a difference how you multiply it. We had a 2 by 3 matrix, so if we multiply that on the right side, might as well try since we have it here. Wouldn't make sense. It's going to give us an error because it's not the right dimension. So multiplying it on the left side, multiplying your matrix by an elementary matrix on the left side would do exactly what you did to that elementary matrix, to that A matrix. Yeah, when you see capital E, first of all, you have to determine what size is your matrix and then what the row operation is, and then you can pinpoint exactly what your E is going to look like. A little bit different. Yeah, so these are elementary, and so the shear is one elementary row operation, so to speak, but it's not, we don't want to think about it that way. Yeah, which type it is, and then try to identify. And then the first thing you do is figure out what size your matrix is, because this is an example on 2 by 2, but this could be, a 4 by 4 matrix. Yeah, what size the E matrix is, and depends on the identity matrix. Depends on the size of A to begin with. Yeah. Yeah. So I think that's what Jessica was trying to say. It's kind of like a transformation on the matrix itself, but generally you don't want to think about it as transformation. I don't know. Nate? So that's what you were saying, right, Byron? Like writing this as row 2 and row 1, writing this as, yeah. Yeah. So if you want to think about it that way. Now this third paragraph here, each elementary matrix is invertible, and its inverse is the same thing. It's the same type, not necessarily exactly the same thing, but it's the same type. So an inverse is something that you multiply a matrix by to get the identity, right? So let's take E1 for example. E1, you switch the row and you switch 2 rows from the identity. So how would you get back to the identity? Do you understand my question? How would you get back to the identity if I took the identity and I switched row 1 and row 2? What do I need to do to go back to the identity? Do it again. Switch row 1 and row 2 again, right? So this is saying that E1, it's the inverse of E1 should be itself. right? Which is to say E1 times E1 should equal to the identity, right? So the inverse of a row swap is itself. So that's not going to quite work out with the other two, but let's figure out. Yeah, so it's still the same type. So if I, so let's take a look at elementary row operation 2. If I multiply the first row by 2, if I multiplied the identity matrix, if I multiplied the first row of the identity matrix by 2, how would I get back to the identity matrix? Multiply it by 1/2, right? So for my E2, if I do another E22 and then multiply the first row by 1/2, I would get 1/2 0, right? For my first row and 0 1 for my second row because it doesn't change. So 1/2 0 0 1. So now if I multiply E2 times E22, I should get the identity. And backwards, E22 times E2 should also be the identity. So they're inverses of each other. Yeah. So let's take these examples that we have for these 2x2 matrices. We can find E1 inverse is itself. We can find E2 inverse as the same row operation, except you're going to multiply, instead of multiplying by the original scalar, you're going to multiply by the inverse, or the reciprocal of that scalar. And then for the third one, if you would imagine how this would work, I need to get rid of this s. So I would multiply the first row by 1 over s. No. I would multiply the first row and add it to the second row. I would multiply the first. If I want to get rid of this s, what I need to multiply by? No. Negative s. We got caught up with inverses. So 1 over, let's think about 1 over a number as the reciprocal. I know a lot of people think of it as the inverse. Like the inverse of 2, you think about that as 1/2. But let's try to think about 2 to 1/2 as reciprocals and not inverses, and let's try to save the word inverse for something like this. So elementary row operation 2, you're multiplying by the reciprocal. Elementary row operation 3, you're involving a negative, not because the negative is really an inverse for addition, right? So you're still doing some sort of inverse there, except we don't think about it as inverse. We think about it as negative or opposite. So the word inverse, I think it's a little bit overused, especially when you're honing in on specific examples like addition and multiplication. So these are your elementary matrices. Your elementary matrices are simple matrices that come one step away from the identity. You did one thing to the identity and you have an elementary matrix. Now, if you do more things to identity, then it's not going to be elementary anymore. You're only allowed one thing to do to the identity matrix to make it an elementary matrix. Okay? So this is going to bring us to the algorithm, which I'll put and talk about for the last 2 minutes, and then we'll continue to talk about it next time. So there's another. What's this say? Oh, Oh, this is kind of related to the algorithm. So I'll put both of that in the notes, and then we'll re-copy that into our notes next time. So the algorithm for inverses is based on elementary matrices. So the theorem says if you have an m by n matrix, it's an m should be an n by n. N by n matrix is invertible if and only if A is row equivalent to the identity. That means you can do a bunch of row reducing to the A matrix and eventually get to the identity. And in this case, any sequence of elementary row operations reduces A to the identity, also transforms the identity to the inverse. So this theorem would make a lot more sense after we do an example, and the example is going to come from this algorithm. So what we want to do is we want to put the matrix A next to the identity matrix. So instead of just augmenting it with one extra column vector, you're going to actually augment it with another matrix, but the matrix is the identity. So you're going to perform your elementary row operations on this new twice as large matrix until you get the identity where A used to be. And once you do that, then what your identity used to be has now become the inverse of your matrix A. It's 2 o'clock. Ah, let's see. N equals A. Oh, did you know that identity is I? Identity is I. RREF and 2, 1, 3 halves, and negative 1 half. All right, that took like 30 seconds. See you guys Wednesday.